So this video is going to cover Module 7 in Wiley's book on acid-base equilibrium. And I'll kind of start in a reverse order. He gives you the Bronsted-Lowry acid-base definition at the beginning of the module, and then at the very end, he mentions the fact that there are Arrhenius acids and bases and Lewis acids and bases, and then directs your attention to think back through what you had studied. So I'm just going to start off with all three definitions of acids and bases, and then work the other way, use that. So Arrhenius acid and Arrhenius base is defined this way, that any substance that if you dissolve it in water, it increases the concentration of the hydrogen ions or the hydronium ion in solution, that's going to be an acid. And a base is a substance when dissolved in water, it increases the concentration of hydroxide ions in solution. So that is the most fundamental definition of acids and bases. And for the most part, we don't use that one because the Bronsted-Lowry acid and base theory is a little more useful to us when we're dealing in liquid water solutions. The Arrhenius acid solution, the Arrhenius acid and base theory, sorry about that, it's limited because it applies only to aqueous solutions. Now the Bronsted-Lowry and base theory, it's a little broader. You don't have to have an aqueous solution for it. You define acids and bases in terms of something being a proton donor, like an acid, and something being a proton acceptor, like a base. And in the way Wiley covered the material in the book, he dealt with all acids and bases in that regard. It's nice to know that you don't actually have to have aqueous solutions. In our example here, this could be, the first example is written as an aqueous solution because we have an ammonium ion and a chloride ion that would be in solution. But that same reaction with the same acid and the same base could occur in gas phase, and it would produce this white cloud above your solutions, the ammonium chloride cloud. So that is the Bronsted-Lowry acid and base theory that you've been working with all along in this module. Lastly, though, he just brings up at the end the topic of Lewis acids and Lewis bases. Now, technically, all of the Arrhenius and all of the Bronsted-Lowry acids would be considered Lewis acids. But we're still going to maintain a distinction because it's going to be helpful if you're just doing proton donation and accepting that we'll still call those Bronsted-Lowry acids. But technically, even they fall under the Lewis acid and base theory. So quick definition here, Lewis acids are electron pair acceptors. So when we're dealing with Bronsted-Lowry, we're talking about something that is a donator if it's an acid, and that's the proton you're donating. But here we're saying that when a bond is formed, if you have an electron pair acceptor, that species in the bond is going to be the acid. And so all Arrhenius acids and Bronsted-Lowry acids will fall under that category. But it's much broader than that. Things like transition metal cations, they also will fall into that. You can see they're positively charged, so they would be delighted to hang out and form a bond with a negatively charged species, and so those are going to be acids as well. All molecules possessing an atom with an incomplete octet of electrons would be. So the example down here is the boron trifluoride. So here, boron trifluoride is actually a molecule, but it doesn't have a set of electrons here on the other side. It would be happy to have an octet and not just 6 electrons around it. And so in that case, that is going to be the receiver of these the pair of electrons. And so we have our Lewis base, which is going to be our ammonia, donating those pair of electrons, and the boron trifluoride actually accepting that pair to form that bond. And so in the Lewis acid and base theory, you're always looking at the bonds that are formed as a result of the acid-base reaction and identifying who accepted an electron pair and who donated an electron pair. So that is the definition of our Lewis acids. Now, Lewis bases, they're electron pair donors. So all anions, like the hydroxide ion, the fluoride ion, this oxygen ion, all those anions are going to be donors because they have available non-binding pairs of electrons that could be used to form a bond. All right, let's look at some examples of acids and bases, and we'll look at this one, aluminum trichloride plus the chloride ion going to aluminum tetrachloride. Which is the Lewis acid and which is the Lewis base in this reaction? Obviously, we don't have a proton being donated or accepted, so we're going to be dealing with Lewis acids and bases. So the way to answer this is you draw the Lewis structure of aluminum trichloride, and then the Lewis structure of the chloride ion, and then the Lewis structure of the aluminum tetrachloride, and from there you identify who was the electron pair donor, that would be the base, and who is the electron pair acceptor, and that will be the acid. So I will let you do that on your own. All right, let's look at a practice here. Here we have ammonia gas, reacts with different reagents, and what we're going to try to ask and answer is ammonia acting as an acid or a base in those reactions. So we start off by looking here. Ammonia combines with water. Well, according to the Arrhenius theory, anything that increases the hydroxide ion concentration in solution, well, that would be an Arrhenius base. And so, sure enough, we increase the hydroxide ion concentration, so we know it's an Arrhenius base. Is it also a Bronsted-Lowry base or acid? Well, the Bronsted theory says that ammonia is going to become ammonium, and it's going to accept a proton if it's the base. And sure enough, it becomes a base according to the Bronsted-Lowry theory as well. Now, the water, of course, is going to donate one of those hydrogen to the ammonium ion, and so in this case, water is going to be classified as a Bronsted-Lowry acid. It wouldn't be considered an Arrhenius acid because water in water doesn't increase the hydronium ion concentration, but it would be in terms of the Bronsted-Lowry theory. And then lastly, we'll just ask, is it a Lewis acid or a Lewis base? And what we said originally is that technically all the Arrhenius and the Bronsted-Lowry bases, they will fall under that umbrella. And so the only thing to do here is identify that you have your ammonia with a non-binding pairs of electrons, if you drew the Lewis structure, that is available to receive that hydrogen from the water, and then in that case it would classify as a Lewis base as well, and it would classify as a Lewis base. So there you have just a simple practice of thinking through all three of these different definitions and then how they come into play. So I will leave the next one for you to ask and answer the same set of questions, the ammonium and the hydrogen chloride as you produce ammonium chloride. As we move on down, in this reaction, you have the cyanide ion reacting with water to produce hydrogen cyanide, plus increasing the hydroxide ion concentration in solution. So our question is this: as you carry out this reaction, the cyanide ion, is it going to be an Arrhenius acid, an Arrhenius base, a Lewis acid, a Lewis base, or a Bronsted-Lowry acid or base? Think through that and answer that question about the cyanide ion. So we'll first think about the Arrhenius acid or base. If it's an Arrhenius acid, it increases the hydronium ion in solution, and we don't have any hydronium ions produced, so that can't be the case. But if it's an Arrhenius base, it increases the hydroxide ion solution. And sure enough, so the cyanide ion is an Arrhenius base. All right. Now let's ask, is it a Lewis acid or a Lewis base? Obviously, it's going to be if it was an Arrhenius base, let's see if it's not also, let's see why it is also true that it's a Lewis base. If we draw out the Lewis structure of the cyanide ion and then the hydrogen cyanide molecule, what you find is that you have a triple bond between the carbon and the nitrogen, and then you have a lone pair of electrons on the other side of it. When you form the compound, hydrogen cyanide, that cyanide ion, it donated that non-binding pair of electrons to form this hydrogen cyanide molecule. And so here we have an example. Yeah, we have a Lewis base as well. Is it a Bronsted-Lowry base? Did it donate a proton or receive a proton? And sure enough, we have the water that donated the proton. We had the cyanide ion that received it. So that's how we think through the different definitions of acids and bases and what they can classify as. Here, really quickly, we'll say something about conjugate acids and conjugate bases. So we're going to abbreviate, or just the definition or the writing of an acid, just say that the acid has this hydronium ion on it. It could be any acid you want. It could be hydrogen chloride. It could be sulfuric acid, nitric acid. It doesn't matter, whatever acid. But it has that proton that's associated with it to donate. And the base is going to be something that could accept that proton. So conjugate acids and conjugate bases are when you go beyond the direction of the equation. We go to your product side. On this other side, if this was a conjugate, if this was an acid on this side, once it loses that hydrogen, it then becomes what we call a conjugate base. It is the associated base of that acid. And you can see, because it's the acid with a negatively charged, it could, depends on its, how desperate it is, it could actually receive a proton. And so that's why this arrow goes both ways. The base in this case is the water molecule, and on the other side of our equation line is going to be the molecule that's formed as a result of the acid-base reaction or neutralization, and we're going to call that the conjugate acid of that. So here we have a species that is positively charged. In other words, he could donate that proton if he wanted to now, rather than receive it, and in that case, he would be considered an acid. So the conjugate acid of a base is you just write the formula of the base, and then you add the hydronium ion that's accepted it, that it has accepted. The conjugate base of an acid, that's the part of the acid that's just left over after it's given its hydronium ion. So go through and write out the conjugate acids for the following bases. In this case, these are bases, so they are all going to be receiving a proton. And then write out the conjugate bases for the acids. These are all going to be donating protons, and I'll let you do that. One of the other definitions that you encounter in this module is the idea of an amphoteric acid or a base. And water is an example of that. It is a very weak acid or a weak base, and so it can function as either an acid if it's in the presence of a strong base, or a base if it's in the presence of a strong acid. And there are other examples of that too, but just to know that that is the name of that molecule. They are the weak acids or the weak bases that can function as either an acid or a base. The next idea to cover is the idea of autoionization. So water will automatically ionize into hydronium ions and hydroxide ions, and in exactly equal proportions. It should make sense to you, because if you break up a water molecule, for every one hydronium ion is liberated, you're going to have one hydroxide ion that is also in solution. And the ionization constant of water is very small, which means that you don't have very many hydronium ions or hydroxide ions in solution. It's a low concentration, but it's there. And so the ionization constant for water is 1 times 10 to the negative 14 at 25 degrees Celsius. That's something that you want to memorize. What that means is that each of these, the hydronium ion concentration is going to be equal to the hydroxide ion concentration, and they're each going to be half of that in a neutral solution. So that's one of the things to memorize, because it is all about, when we talk about the pH of a solution, it's all about whether in a solution you have increasing or decreasing amounts of hydronium ions or increasing or decreasing amounts of hydroxide ions. If you have a hydronium ion concentration that is higher than 10 to the negative 7, then it's going to be an acidic solution, and it's going to have a pH that is less than 7. If you have a hydronium ion concentration that is less than 10 to the negative 7, then that means you have more hydroxide ions in concentration, and it's basic, and the pH will be greater than 7. Here's some more equations to memorize. You want to be able to know that the pH of a solution is equal to the minus log of the concentration of hydronium ions in solution. And the hydronium ion in solution is going to be written as nothing more than 10 to the negative pH of the solution. That's how you can calculate the hydronium ion solution if you're given the pH. We can also talk not only about pHs, we can talk about POHs, and it follows the same pattern. The concentration of hydroxide ions in solutions, if you take the negative log of that, that is what we call our POH. And let's say you're given your POH, you could calculate the concentration, because the negative of the POH, take that to the times 10, that'll give you the concentration of your hydroxide ions in solution. And if you know what your pH is, then you could add that to your POH, and that will always give you 14. So if you don't know what the POH is, but you know what the pH is, you can just take 14 minus the pH, and that will give you the POH. And you're familiar with the pH scale by this time. As the hydroxide or hydronium ion concentration decreases, the pH increases, and the scale looks like this. It roughly goes from 0 up to 14. Technically, you can have a pH that is less than 0, even negative, and you can have a pH that is greater than 14, but usually the scale is written just like this. So the problems here are just plugging the numbers in. I'm going to give you problem number 1. I give the POH of an aqueous solution is 4, so I give you the POH. You are going to then calculate the concentration first of the hydroxide ions in solution, and then from that you can subtract that from 14, and that will give you the concentration of your hydronium ion in solution, which is what this question is asking. So I'll leave these problems for you to do too. Next thing we'll talk about is the strength of an acid or a base. So acids can be strong acids, or they can be weak acids, and it has everything to do with percent ionization in solution, how many hydroxide ions or how many hydronium ions are produced. So an acid is considered strong if, for the most part, it completely ionizes in solution. It gives up all of their hydronium ions to the water solution. If you have a bunch of hydronium ions in solution, that makes it a strong acid. And so a strong acid is strong if, in a sense, it falls apart really easily. In other words, it donates that proton very easy. And there are a lot of strong acids. There's hydrogen chloride, hydrogen bromide, hydrogen iodide, nitric acid, sulfuric acid, chloric acid, and that's a hyperchloric acid. Those all will have equilibrium values, Ka values, that are large because they completely dissociate. An acid is weak if most of the acid hangs on to its hydrogens, to its protons. For example, acetic acid is the acid that hangs on to most of it. When you dissolve vinegar in water, most of the acetic acid doesn't dissociate, and only a small point of it does. And so that makes it a weak acid. And we can form an equation to work with the acids and bases in equilibrium merely by writing out our equilibrium equation. The acid ionization constant is going to be equal to the hydronium ion concentration times the hydroxide ion, or times the conjugate base, the conjugate base in solution, divided by the initial concentration of the acid. And so here in these practices, I'm just going to have you write out a balanced equation of the ionization and the dissociation constant, the case of A, using these following acids. You don't have to do any math here. You're just writing the equation just like we wrote this equation up here, but you're actually including the acid that's a part of it. And if we look at acids and the conjugate bases in terms of the strength, strong acids always produce very weak bases. And strong bases produce very, very weak acids. Technically, they could be an acid, but it's barely, negligibly. And we have this category in between, these weak acids and weak bases, where they both, neither strong nor weak, and they exist in between the two. And finally, we get to do a little bit of math. We can calculate the pH for strong acids of a known concentration. Because it's a strong acid, we know that if we know the molarity of the acid, then we will know, therefore, the molarity of the hydronium ion in solution. Because it's a strong acid, it completely ionizes in solution. So in the first one, all you have to do is, if you have a pH of 2.56, we calculate the concentration of the hydronium ions in solution, and that will equal the concentration of the acid that we added to the solution. It's different if you have a weak acid, like formic acid. Formic acid is just a little bit smaller of an acid than acetic acid. Here you have a solution of a 0.1 molar solution of formic acid, and you know that you have only a pH of 2.38. So in this case, you'll go from your pH to calculate the percent hydronium ions in solution, and then you will know what, based on the concentration of your initial acid solution, then you can calculate the you could calculate the acid ionization constant. And I'm going to give you the answer there, but you need to go ahead and do all the equations. In acid and bases, we also talk about things that are polyprotic acids. That means it has more than one hydrogen to donate. The thing to notice is not just that there's more than one hydrogen to donate, like sulfuric acid has 2 and phosphoric acid has 3. What happens is that after it donates its first proton, it's less likely to donate its second, and even less likely if you have a triprotic, it would be even less likely to donate that third. Of course, if it's in the presence of a strong base, then every one of them are going to be donated. But if it's just dissolving in water, what you find is that as you dissolve sulfuric acid in water, that first proton comes off really easily, and the acid ionization constant for it is large. We call it, that first one is completely dissociated. But by the time you are dealing with the second proton, it's much less large, and much less of it goes into solution. And as this note points out, usually only the first hydronium ion that comes off in enough quantities to make a contribution to the pH. And so if you can calculate that one, go ahead and calculate for the next hydronium or next proton to be donated. But a lot of times that it doesn't change your actual calculable concentration. So for practice, write out an expression for the acid dissociation constant, the first, second, and third of phosphoric acid. And that's just the equations. You don't have to give me any numbers. You're just writing out the equations for that. And then we conclude with just some nomenclature, writing out formulas and names. So if I give you periodic acid, that's the iodine ion, can you write out the formula for that acid? Or hydrosulfuric acid, what would it look like? Barium hydroxide, nitric acid, ammonium hydroxide, sodium hydroxide. These are all, many of these you're very familiar with already. Over here, I give you the compound abbreviated, and you're going to write out the names for that. A couple of simple review questions. A conjugate acid of water is what, and the conjugate base of water is what? And I will leave you with those problems to finish up. And that is my summary of Module 7.